Okay, let's get started. We've talked about this model, base tone model, and let's think about some example. Example. Okay, it's for the refrigerator. So let's say there is a mean demand for the refrigerator. Let's assume this is a 10 units per month. It's a demand for freezer, and let's assume it takes about a month to fill the order. Replenishment lead time is 1 month. Okay, so manufacturer takes about 1 month to make it. Okay, from here we can easily deduce that the mean demand during the lead time is defined as theta, which is 10, right? 10 units per month. Well, L is 1 month. Okay. And in this basis tone model, we discretized the demand as an integer. So the most simple integer distribution is Poisson distribution. So let's suppose this demand is a random variable, but it follows Poisson distribution. Okay? Demand follow Poisson distribution. Poisson distribution is given as this function f, where lambda is defined as interval and k is defined as occurrence. So k is integer. That's the Poisson distribution, definition of the Poisson distribution. So Poisson distribution basically deals with the probability of a number of events occurring during given interval lambda. If these events occur with a known average rate and independency of the time, is maintained. Okay? It's just Poisson distribution. Okay? Okay. Then let's say PR is probability of demand during lead time L is equal to R. It's the definition, which is same here. Theta R E minus theta e to the minus theta R factorial. Okay. basically theta is the demand, 10 unit. And we assumed in basic tone model, the demand happens one by one. But this 10 unit means that this demand occurs 10 times. Okay? So interval lambda is equal to R minus theta, theta. Okay. 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 Then from here we could derive our GR function like this. Which is nothing more than just okay, and utilizing this we can do some calculation. If R is equal to 0, then PR is 0, then GR is 0, and PR is 10. If R is equal to 1, then it's still 0, 0, 9. If 2, 3, 4, it's about, when the R is equal to 2, it's about 0.002. And it's about 0.003. And it's about 8.001. When R is equal to 3, then it's about 0.008. This GR now becomes 0.010, and BR becomes 7.003. When R is equal to 4, P is 0.019, GR becomes 0.029, and BR becomes 6.014. Okay, let me refresh your mind, and based on the definition, this Px is probability of demand during replenishment lead time. Probability of demand during the lead time is equal to X. So PR is probability of demand is equal to this R, and we assume that this demand is following the Poisson distribution, so it's just straightforward. And based on the also definition, large G function means it's a CDF. This is PDF, CDF. So what we do is the integration. Why this is summation sign other than integration? Because it's a discretized number, right? So that's why. And B function is average number of outstanding backorder, and we derived the equation of the BR in previous courses. Okay, if we do follow this one, you can easily construct your Microsoft Excel worksheet. Everything will be calculated automatically. And if R is equal to 13, 14, this PR is 0.07, 0.052, and this GR is become is 0.864, 0.917, and this BR is 0.322, 0.187. Okay, question. What's the meaning of the function BR? Expected value of what? Backorder. It's a probability or number? Number, average number, expected value of average number of backorder. Okay, you know, it starts from 9, so it cannot be probability. Okay, how about GR? What is the? It's a cumulative probability function, right? Probability of demand is equal to or less than this R, right? You know, we calculated this based on this random demand. Okay? Any questions so far? Okay. Okay, so if we want to achieve a fill rate of at least 90%. Fill rate means 90% of fill rate is, you know, the rate, the fraction of orders that are satisfied by the on-hand inventory, not back ordered, right? So 10% of back order, right? Which means 10% of the demand cannot met instantly. So we can easily regard this 90% as a unit of customer satisfaction or something, right? Okay, we'd like to service level of 90% by this fill rate, and we calculated this fill rate is equal to that, right, in previous class. So what we want to do is we have to have at least 90% of this value. Okay, based on this calculation, well, G function should be somewhere here, right? If this one is, if you know, G13 is 0.864, G14 is 0.917. Okay, we want to at least here, so we should choose 14, right? With 13, we cannot satisfy that. So if we choose the 14, then R should be 15. Okay? What is R, by the way? What's the definition of the R? Come on, guys. What's R? Yes. What is inventory position? It's a kind of account book which represents your level of inventory. On-hand inventory minus back order plus replenishment order. That's the R. Okay. But by the way, utilizing all the formula we've derived so far, now we know that in order to supply at least 90% of service level, we have to keep inventory level of 15. Provided that the random demand follows a Poisson distribution with mean value of the 10 unit, etc. Okay, we've calculated this, and also since the mean demand during the lead time is 10, from the inventory position equation, small r minus theta is equal to this is large R minus 1. So 14 minus 10, 4. It's a safety stock level. And also, based on this, we know since R is equal to 15, P15 is, if we calculate it, it's going to be 0.103. Okay, utilizing this value, we can calculate this IR. What is IR? It's an average inventory level. IR is given as large R minus theta plus PR, and we know everything, so it's a 15 minus 10 plus 0.103, so it's a 503. That's our average inventory level. Okay. Questions so far? What's the unit? Okay. What is the unit? It should be on your lecture notes. IR is, what's the definition of IR? Yep. Average on-hand inventory level, to be more precise, and it's given in unit. So this situation, your on-hand inventory level, the mean value is around 5 units.
And this real goal is to find on-hand inventory or inventory position.
Very good question, and we've talked that part. But what do you think based on this? We'd like to answer how much we should carry. In order to answer how much we should carry, we have to determine when to reorder, right? We'd like to determine when to reorder. And this R is reorder point. By the definition, R is in our calculation is 14. So when you have on your inventory level reaches down to 14, you have to put reorder. Then you can have service level of 90%. If you change this 90% into 50% or something, then your R will be less than that, right? It's your decision. You want a 90%, 95%, 99%? Well, up to you. But based on this model, if you want a 90% of service level, you got to reorder when your inventory level becomes 14. And think of that. You have 14, but you know your mean demand is 10. So in common sense, you're good, right? Average demand happens during the lead time is 10, but you have 14. Okay, why bother to reorder? Because it's a random. The demand is not always 10. It sometimes could be more than that, right? Safety stock level. You have 14, but average demand is 10. You have 4 more for safety. Okay? So, should be very careful. Safety stock is not the base stock. Okay? Okay. If you don't have any question about this model, all the mathematical calculation was already done, and I'm just showing how you can use it. And the interesting part comes right now. Okay. Let's go back to good old y function. It's a cost function, total cost function. In EOQ model, we've calculated y function of q. Q is the economic order size. Now we are going to deal with R, which is very closely related to the reorder point, and thus very closely related to the how much stock we should carry. And the reason we calculate the total cost is always to find out the optimal R. Okay? Let's say it's always holding cost plus, in EOQ model, it's a inventory cost plus ordering cost plus production cost. And production cost does not have any term, Q term, so we can easily cancel that out. Because anyway, if we differentiate it to find the minimum value, it does not have any effect, right? But in this base stock model, we are comparing holding cost, which is the inventory cost, plus back order cost. Let me ask why? Why don't we consider replenishment order cost in this model? Why? It's natural to consider inventory cost, right? And in this Bayes-Stokes model, we introduced the concept of backorder, so we have to consider that backorder cost. Why not replenishment order cost here? It's because of the assumption. We assume that the order happens one by one. We are dealing with how many times. Okay? So we don't have to consider, putting one order of 10 versus putting 10 orders during the same time. That was the question in previous model, but not the question here, because we assume that every order should be put one by one. So that's why we don't consider replenishment order cost. Okay? Okay. Based on many parameter definition, the holding cost can be calculated as the holding cost per unit per time, which was H, and average on-hand inventory, right? Which was given as IR. And backorder cost should be also some parameter of cost of carrying 1 unit of backorder from given period of time, which was we defined as a B, and the average number of outstanding backorder, which is PR. That's why we define these weird looking functions in upfront of this Bayes-Stokes model. We did that because we want to use that function in this form. Okay, let's do some mathematics. H times IR is like this. Can be substituted with R minus zeta plus PR. And there is another PR. And if you do some cleanup, it's H R minus zeta plus P plus H PR. Okay. Well, in order to find the minimum cost, we will do the differentiation with respect to R. And we have R term there. So let's do the differentiation. DYR dr first term. If you differentiate this with respect to R, only H remain. H plus, well, this one doesn't have any R, it's just constant. So B plus H dBr dr. Okay. This model calculation of the minimum value is a little bit complex because we have to deal with this type of function. And the BR is the average number of backorder, remaining backorder, and the definition of the BR function is in previous note, I introduced the BR like this. That's the definition of the BR. Well, now it's a little messy because R part is here. If you don't have any R in this summation sign, you can just easily apply this differentiation sign inside of this one. But now you have R. It is really messy. So we'd like to introduce a little approximation tricks. Okay? The trick is like that. We transform our BR function into continuous version, which is like this. The difference is now x minus r part remains same, but we introduce the small gx instead of this px. Okay? Which will take care of all these transformations. Okay? And what is the definition of the small gx? The meaning is exactly same. In previous model, because in previous model, Nussbander model, it's a probability density function. And we assume that continuous PDF function. But now this px is also same old PDF, but not continuous version. So we just transform everything into continuous version, but the meaning is exactly same. If we utilize this kind of transformation, then dBr over dr is now simpler. We can directly apply this differentiation to the function, which is if you do the mathematics, you will end up this function. Too simple, right? And this is, by definition, the large g function is the integration of the small g function by definition. Okay, go back to the original form. So dyr over dr is h plus b plus h with that one, and we plug that one into the original form. It's going to be this. And if we like to find the minimum cost, we can equate this slope equal to 0, and you know, now it is much easier to calculate how we can satisfy this one. Well, you can put this h to right hand side and minus as well, this and minus 1, and you know, if you do the trick, if gr is equal to then it's it's going to be some value. And as we did before, if we calculate tables of GR with varying R value, and we can match that R, which is like this, then this R is the inventory position, which will minimize your total cost. It could be different from the 15 we calculated before. That 15 is the minimum inventory position in order to maintain at least 90% of service level. But this is the, without that 90% of service level consideration, we just briefly calculated what would be your optimal inventory level. Okay? Okay. How these two examples are different? Well, I think this one is more robust. You know, sometimes in real world, people want to set the 90% of service level or just 1 minute of waiting time. That's maximum, no matter what. This approach is also possible. But in this model, we can cleverly determine the B. You know, if the B, the cost of backorder getting larger and larger, automatically the optimal inventory level and the service level will be increasing. So you can model the 90% of service level with this B value, manipulating this B value. Or, okay? Another example. Now, the two guy at Changwon lost the connection, so I don't know. It's not my fault. Okay. Let's think about this case. And standard deviation is and wholesale cost and let's say the holding cost is interest rate of 2% or something, 2%. So holding cost is 2% per unit per month, which means exactly 0.02 times in real world, inventory cost is calculated with interest rate. Okay? If you have your merchandise sitting at your warehouse, it's just your money sitting there doing nothing. Right? If you put the same amount of money in the bank account, you will earn the interest. Okay? So that's the inventory cost, kind of. But if we think of some deterioration or rusting or damage or something happens inside of the warehouse, this H will increase. But bottom line is like that. Interest rate is your holding cost. Okay, and let's assume your back order cost B is $25 per unit per month. Okay.
Is it 20% annual tested or?
No, 2% monthly interest. 2% of annual interest is very low, right?
If it has been, if it would have been annually tested, then we will be doing divided by 12 to bring out the monthly interest rate.
Yeah, but this means 2% of monthly interest rate. Okay, if you put $100 inside a bank account and you will earn $2 of interest per month, that's what I mean. Yeah.
If it has been 2% annual, then we have been dividing it by 12 to find out the monthly.
That's not really true because there are several other ways to calculate your interest rate. I know in Korean, but not sure in English. But in Korean, we can 복리 계산. Can you translate it in English? You know, sometimes it is true. Base money is there, okay, $100, and after 1 month you will have $2, and next month you will have 2% of not 2% of not 100, 2% of 102.
Composition.
Oh yeah, composite interest. If you apply composite interest, then it's not gonna be just annual interest divided by 12. You need some more calculation, right? What's the opposite? The other way of is the simple interest and composite interest. It's up to what kind of interest you're referring to. But in here, I just make that it's a monthly 2% interest to make problem simpler. Okay, and let's assume B is $25, and we can calculate this B over B plus H is 0.625. Okay, and now we have to calculate GR, which is equal to 0.625. GR, this is CDF, right? Okay, let's assume then, whatever it is, if our CDF follows normal distribution, then you know how to do that. In normal distribution table, CDF table, you can identify this value and read that value out of it, right? Right? We did the same thing in previous models, right? When we use the normalized normal distribution function, such as it's a mean value plus I don't know, so you know the trick. Okay, by doing this we can determine what is the optimal, which minimizes total cost, optimal inventory position by doing this. But from this example we got to know the CDF, what kind of CDF we are dealing with. Okay. Let's summarize this long base stock model. First thing to remember is we've gradually released some of the assumptions one by one from the most simple EOK model, and we proceed, and we've now we have dealt with the Bayes-Tong model. And I made a little mistake because on your homework number 3 there is a QR model, right? But we haven't covered it. The next step is that model, but the due date is wrongly assigned. Yeah, that's one thing. We have one more thing to do by relieving one more assumptions. And in research area, not this course area, in research area, we have still lots of things to do because we have still many assumptions, many strong assumptions. Okay? Based on this derivation, we can say that reorder point control by defining small r or large r, those two values are differentiated by 1. Reorder point, the r value, controlled the probability of stock out. Stock out means everything is sold out and you don't have anything left. So probability of stock out by establishing safety stock. You remember that the mean demand during the lead time in previous example was 10, and we have 4 units of safety stock. Okay? So the reorder point was 14. The safety stock of 4 means, well, the mean demand is just the mean. The demand could be fluctuate because it's random. The safety level, safety stock. And reorder point controls the probability of sold out. Okay? It could be from preset 90% of service level or, optimal cost and the like. Okay. Any question and comments? And I keep insisting that you got to clearly understand the assumptions. Okay? If you clearly understand the assumptions and terminology, the mathematical derivation is not that complex in our model because I'm just covering the simple inventory control model. Okay? Okay. Have to, you got to understand what's going on. Okay, let's think of this QR model. It's a little bit more complex model, and this is about how much. This model is about to answer how much stock to carry. Same as the Bayes-Tong model, but with this model we have to answer one more question: how many to produce or order at the same time? In Bayes-Tong model, we assume that we are only interested in how much stock to carry, and assumed the replenishment order is put one by one. But in this model, it's more realistic compared to the Bayes-Tong model. It is interested in how much should we carry and how much do we have to put order at the same time. Okay? A little bit more to the real case. Okay? This is for how much stock to carry. How many to produce or order at a time. And as we always did, since this is model always have assumptions. Assumption is saying except fixed cost associated with replenishment order. The interesting part is here, or not and constraint on the number of replenishment order per year. This model works with the identical assumption with Bayes-Stokes model and this or this. You have fixed number of replenishment order. You can order some fixed number of replenishment order or less than that, or the replenishment order has the fixed cost associated with it. So it's quite realistic to know. Okay. And with this assumption, there is as the model, the assumption is relieved step by step. So the model approaches step by step to a more realistic case. We have to introduce some new concepts, like a back order, or inventory position, or a safety stock, or something like that, based on model, or etc. Let's say there is a cycle stock and safety stock. Cycle stock is defined as, it's an inventory basically. Inventory that is held to avoid excessive okay? If reorder cost is too high, or if you buy bulk, you will get discount, which is a minus cost, right? Benefit is minus cost, negative cost, which is good to us. So because of that, we could buy more than that, more than we need. And those stock is we define cycle stock. Okay? And safety stock is same as the safety stock in Bayes-Stokes model. Inventory held to avoid stock out. Okay. Cycle stock. If we only consider cycle stock and inventory cost, then it's EOQ model. You know, EOQ model, we are trading off the reorder cost versus holding cost. If the holding cost is cheap and the reorder cost is high, then we can order many amount to stock. And so basically speaking, the inventory dealt in EOQ model is all cycle stock. Okay? Safety stock. Well, in base stock model, we assume that everything is ordered one by one, so we are not considering the replenishment order cost during the calculation of total cost. And we discussed the reason. And but in inventory level calculation, what we are concerned about in base stock model is sold out, I mean the stock out. We got to have some safety margin or reorder point. So in base stock model, the inventory we will discuss is all safety stock. In that, if we contrast the differences between these two, base stock, EOQ model. But now QR model, we are considering both of them at the same time. Okay? Okay. In this model, what we'd like to do is minimization. Minimization of this fixed setup cost plus backorder cost plus holding cost. By this QR is your design space, your decision variables. By cleverly choosing Q, it's the same Q as in EOQ model. The how much order at the same time, Q, and R is your reorder point, the same as the base stock model. But in this QR model, now you're considering both at the same time. Okay? Okay. In base stock model, we didn't consider this. In base stock model, the Q is out of consideration. But we are kind of minimizing this total cost to find optimal Q and R at the same time. Or, why or? Because identical assumption with this or this. Fix the cost, fix the set of cost. Okay? So, okay. Same. Your decision variable, design space is Q and R at the same time, but it's the same thing. However, now you're considering stock out cost. In a broad sense, these two costs are essentially same. The cost of when demand is larger than your current inventory, backorder cost in some sense, or stock out cost in some sense. So for some product, then you can put backorder, then you can use this one. But for some other product, there are some products that you cannot put backorder, then you cannot just. It could be lost sale cost, such as in news vendor model. Okay, like this. This is OR, but not OR, but anyway, fixed cost you can easily apply here, right? Constraint on the number of replenishment order per year could be those things also can be considered in this two model. Okay. Okay. The approach is always same. We introduce the assumption and what problem we'd like to solve, and the next step is introduction of long and boring parameters. Okay, notation. D is defined demand. But to be more precise, let's say expected demand per year or per given unit of time. So given in unit, L is same as in Bayes-Stone model, replenishment, lead time, and X is demand during L, and also this is random variable as in Bayes-Stone model. And can you see the difference? It's X demand during L. D is expected demand, it's a mean value per year or per given some time, but not specifically per lead time, okay? Okay, and theta is expected value of demand, okay? Question, Q, theta and D, are these two values same? No. Okay? If we stick to this year, and let's say this L is given in days, for example, this is DL, right? So the point is D is different from theta, okay? And the sigma is standard deviation of your random variable demand during L. And let's continue over here. And small px is probability density function. It's a probability that demand during the lead time, large X is the demand during L, demand during the replenishment lead time is equal to X. It's a PDF. And large GX is probability of this. Equality sign comes in, now it becomes CDF. So in word, we can say that the demand during the lead time L is equal to or less than some value X. Okay, it's a CDF, and basically it's a summation of, right? And large A is, as in EOQ model, it's a setup cost. Or two things. Setup means what? The cost related to the, when we put replenishment order cost, right? That's the setup cost, right? Order cost. So unit is but the orders doesn't have any actual unit, so actual unit is dollar. Small c, same as in EOQ model, is production cost. Dollar per unit. Small h, this is holding cost, but X is about during L, but D is about annually. So for now, let's stick to annual time span. Annual holding cost. You can scale it up to the quarters or month or weeks as you want. As you want. Dollar is the unit. Sorry. Dollar per unit per year. Okay. K, new variable, cost per stock out. Since we are in second alternative is the setup cost plus stock out cost plus inventory cost, we need something to represent the stock out. It's given as dollar per number of stock out, so which doesn't have any unit, so it's a dollar. And B is, let's keep annual time span as it is. Annual unit back order cost, dollar per unit per year. As in base stock model, B is about back order, H is a holding inventory. Okay, and Q, amount of the order, so replenishment quantity. And this is our decision variable. And R is, as in base stock model, it's a reorder point, also given in units. This is also our decision variable in this model. And S is defined as R minus theta same identical to the base stock model. It's a safety stock. And we have the same functions s. Now it's a, since the decision variable are q and r, so s is now a function of q and r, fill rate. And definition of the fill rate is same as in base stock model. Fraction of orders filled from stock. And we need the same b. But now in this case, a function of q and r. This b is average number of outstanding backorder. Same as in base stock model. Okay. And as in the base stock model, we need I. Now in function of Q and R is a average on-hand inventory level. Now we need one more. It's a new concept introduced here. Since in the introduction of this Q and R model, two things. Setup cost, fixed setup cost, or there is a limitation on number of reorder. So FQR is order frequency. Given, for example, how many replenishment order you put per year or something. Okay, once we defined all these required parameters, let's think about cost. Okay, first, fixed setup cost. Even though we have the replenishment or the lead time L, let's think everything in per year as a, let's say this per year. Year is our planning horizon. So how many order do we put per year? It is F, right? So F, also a function of QR, times, if we multiply that one with A, setup cost per order, then it's annual setup cost, right? Okay? And one more thing to consider. Frequency. How do we define this frequency? Well, we said D is the expected demand per year. And we said Q is number of replenishment units per order. So as in EOQ model, if we divided D with Q, it's a number of reorder per year, right? Simple, right? So we can assume this is Q and I. So this one becomes D over Q times A, which is annual fixed order cost. Which is exactly same as in EOQ model. Okay, time's up. So I have to define stock out cost and all other probability. And okay, because we haven't covered the QR model until today. It's the last class before the exam. So your homework number 3 are due date is postponed until we cover QR model. Okay, I don't know what the date will be, and I will say that this QR model is not the, not in your range of midterm exam. Okay, fair enough, right? But in your midterm exam, everything covered so far until base stock model will be your range. Okay, and as we discussed in previous class, on Monday, TA and I will be around here, so you can freely come to this lecture room and ask questions. But if nobody shows up, then that is also fine. Okay? Okay? Thank you.